Okay, ladies and gentlemen, as we get started here today, I can't tell you how pivotally important the last few lectures have been about setting states, about figuring out where we are, about finding properties. That is going to be the key bit of information that you are going to use in almost every problem from now on in this class. So if you're having difficulty, if you're saying, man, I don't know how to solve that, or I don't know how they found that property, or you're anytime in here you're thinking sure, that works, but I didn't quite get it. Let's figure it out, because if this is the weak point from where you are in this semester, it could be a very big weak point. Okay, so what we'll do now today is I want to start off today by talking about and setting a property setting flowchart. So I like to, when you're getting to a situation where you're getting a lot of information, and I dumped a lot of information to you, that you have now a way to work through thinking about how to solve the problem. And so this is going to take if you have an 8.5 by 11 notebook, I'd put it on its side here as we're going to look at this. I'm going to use a whole wide sheet of paper here. Here's what my flow chart looks like here, on the wide sheet side. But what you're going to set here is you're going to come into a thermo problem. Okay, here's your thermo problem, and we'll put a box around that. And when you have that thermal problem, the first thing you have to ask yourself is, does mass, is it cross the boundary? That's the only question you ask yourself, does mass cross the boundary? And if the answer is no, well, then you have a closed system. Okay? If the answer is yes, then you have an open system. That's the only question we ask. Is mass cross the boundary? Now, right now, all we have done was closed system, so we don't have to ask that question to you right now. Now you're automatically going down to the closed system set, but that's just letting you know that's the decision that we're going to make. And then here with this closed system, now what we're going to do is we're going to say, well, we're going to draw out the equation, delta KE plus delta PE plus delta U is equal to Q minus W. That is let me put it in a little bit more general terms. The summation of the heat transfer minus the summation of the work. That is the governing equation that we'll have for this. And we'll have to make our assumptions and models here. What model we're going to follow. We're going to ask ourselves those questions. Maybe we're going to have that heat transfer is equal to 0. Maybe we're going to have work is equal to 0. Maybe we're going to have work is equal to the integral of PdV. Okay? Maybe we're going to have kinetic energy and potential energy is equal to 0. These are all the questions that we're going to ask ourselves here. Okay, and once we do that, once we get all those questions answered, we're going to have to set the state. So here we're going to go set the state. Now, actually, when we get through our open system, we're also going to have to set the state. So really, the set the state kind of joins up it comes back down here and joins up, and we're going to have these two things that are going to intersect here. So setting the state is going to intersect for both of them. We're not going to set the state differently for open systems, but we're going to ask ourselves a whole bunch of different questions here in our equations. In fact, you know what? Actually, what's going to happen, because tomorrow we're starting chapter 4, I'm really going to only introduce to you really two more, I should say that. Three more equations this semester, 3 more big equations. And there's lots of sub equations that we're going to deal with, but really 3 more big equations. And the first equation that I gave to you that's really big is this one here. This is one of the big equations. I'm going to introduce to you the first law for an open system, the second law for a closed system, and the second law for an open system, and everything else kind of just feeds right into those things. Okay, now setting the state. Setting the state, where we're going to. Setting the state, there are some things that we can do. First thing let's look at, okay, what happens if we look at the state, and what we're going to do to set the state is we're going to draw our PV diagram or TV diagram figure out where saturation is, and figure out if we're above or below that. So this is all in here. Let me say that we're going to draw. I'm going to make this little line. We're going to draw our saturation curve, and we're going to find out what we are. Okay, so that's my little symbol there. Okay, and the first thing we're going to look at is if we're a solid. Now, we're not going to be able to find the solids through this little TV or PV diagram. We're just going to know it's a solid because it's solid. It's iron. It's copper. It's aluminum. The only thing we can do with that is the incompressible substance model. That's the only way we can solve these problems and get the properties is using the incompressible substance model. There's no other way to find our properties. None. In this book, anyway. There's probably books that you can find that, but this book, only way we can do that. Okay. The next thing we could find that it's a liquid. We could find that on our vapor dome that it's to the left of the vapor dome, and it's a liquid. Okay. Now, the liquid, what we could use is we could use the incompressible substance model, because liquids are incompressible substances. So if you are a liquid in a state, you can find the incompressible substance model. And usually we have to make sure it's your liquid in both the start and the end state. That's when you'll do your incompressible substance model. This is one thing we do, incompressible substance. The other thing that we could do, we could go down here, we could say, well, we could also do the liquid approximation. Okay, that is given to you as you approximate the properties as if they are saturated liquid properties at the temperature that you've been given. I'm not going to really go into all that detail in this box. I'm just going to say, hey, refer to the liquid approximation. Or if you're water, oh, that's terrible. Just turn your worksheet to the side, Wanklin, and type it in here. Water. My handwriting is bad enough on this tablet. If we're water right there, we can go and we can do the compressed liquid table. Okay, if you're water and you are you have water, I should say here. Let me just put this. We should say water at high pressure. Means they're greater than 25 bar. We can go to the compressed liquid table. Otherwise, we're going to use a liquid approximation. I mean, very few times do we use compressed liquid tables for water. We use liquid approximation or the incompressible substance model quite often with water. But I want to show you all your options that you can do here. Okay. What's the next thing that we can have in here? Well, you can be a mixture. I'll write here a liquid vapor mixture. Okay, that's the next thing you can have here. Okay, that means you're inside that vapor dome. Okay, there, what you need to find is you need to find the quality. You need to find the quality. You need to find the quality that tells you, my handwriting. Really disappointed in my handwriting. You can find the quality that tells you how much of your mixture is liquid and how much of your mixture is vapor by mass. That's what you can do. And then you're going to look this up in the table. Okay. Every substance there, this is going to be for ammonia, propane, R134A, R22, and water. Those are the 5 things that you're going to have liquid vapor mixtures in this class. Ammonia, propane, R134A, R22, and water. That's what you'll do. And then the last thing that we'll do is if you're on the other side of that dome, vapor dome, you are going to be a vapor. Okay, now let's see what our options are with vapors. Well, you can look at yourself and you can type first, say you are a real gas. Or you can say you are an ideal gas. And how do we find out if we're a real gas or ideal gas? Well, here we have to check. I should probably put this beforehand. Erase everything I just said. First thing I want to say is generalized compressibility chart. No, that's not what I want to say. I have my notes here. I'm really struggling with what I want to tell you because there's really two options that we choose here. And so I'm going to go with kind of how I have it written here. I think you'll understand what I'm trying to say here in a minute. If we have a vapor, we can one of our first choices is we say, well, it's superheated. And we're going to go to the table. Okay. We're going to do this for the same things that we did for our liquid vapor mixtures. Water, ammonia, propane, R134A, R22. We're just going to say it's superheated. We're going to go to the tables. Okay. Now, if we go here, we say it's always a gas. Okay, so I'm going to say here, always a gas. Or I'm going to say usually a gas. If it's usually a gas, water is not always a gas or usually a gas. Ammonia, propane, R134, those can be liquefied. We see them all the time liquefied. That's where we go down this superheated path. But if it's usually a gas, we have to ask ourselves, do we want to look at it and call it a real gas or an ideal gas? Well, a real gas, here that means Z is not equal to 1. Okay, real gas Z is not equal to 1. And what we would use in that case is we would use our generalized compressibility chart. Okay. And if it's an ideal gas, we are going to say, well, that's because Z is equal to 1, and we're going to follow a model. And what we can do with the model, we can say PV is equal to RT. Okay? And in here, we have a choice. We have a choice right here. We can say, well, does the ideal gas, are we going to model it as a variable specific heat? Or are we going to look at this as constant specific heat? And if we're doing variable specific heat, what do? We use the tables. And for constant specific heat, we're going to say that delta U is equal to C sub V delta T, and delta H is equal to C sub P delta T. Okay, that's how this goes. Look at all these decisions we have to make when we come down to a vapor. Vapor becomes quite interesting that we have here. Now, I've kind of modified my table that I have in my notes here, as you can see, real time is live, because it gets, when it comes to a vapor, you have to think through many different processes. And in my brain, I've seen these things so many times that I can draw this, and I could modify this even more detailed for my own purposes. I want you to look at this, and I want you to be able to have it mapped in your brain before we get into chapter 4. It really ended working on those problems. If you can see problems, see states, see information that's given to you, and figure out where to go on this chart automatically without referring to this in your notes, that's where you need to be by the exam that's coming in after the 4th of July here. What is it, 4th? It's 6th of July. You have to have this in your brain. Of course, you just have an open book, open note test. Absolutely. But you're going to run out of time if you always have to refer to this in your notes, okay? Get this memorized, write it up for yourself, add other notes for yourself. Before the next test, if you can just sit down and draw this and make it in the form that works best for you, you're going to be, you have a better chance of being successful than those students that just have to refer to this and not necessarily know exactly what it means. You saw I was over here with the vapor thinking, what should I do? How should I explain this vapor thing? Okay, maybe you say, well, I understand this vapor thing a little bit differently than you do, Dr. Wanklyn, and I like to put it in this other way. Great, do it that way. Do whatever makes you feel best about understanding it, okay? And that's where we'll go. Okay, that's how I want to open today's lecture.